Good afternoon, everyone. I welcome you all in the post-lunch session of the day. And in this session, Professor Debasish Sarkar, MNIT Jaipur, will continue his talk on future potential of supercapacitors. Debasish sir, am I audible to you?
Yes, ma'am. You're audible.
Sir, can you turn on your video, sir?
Yeah, sure. I think it's fine, right?
Yes, sir. So can we start the session, sir?
Yeah, sure. Just give me 2 minutes. There is some problem with my internet network. I have to just switch it to my mobile network.
Sure, sir.
This meeting is being recorded.
Sir, am I audible to you, sir? Please unmute yourself.
Yeah, it's fine now. Am I audible?
Yes, sir.
Okay. Just a minute. I think it's fine now. Okay, shall we start?
Yes, sir. Sir, can we have the presentation on slideshow mode?
Yeah, sure.
Yes. Thank you, sir. It's okay now.
Okay, so welcome back, all of you. After this heavy lunch session, I don't think you are feeling gloomy this time. So I'll try not to make you bored and try to have some nice and interacting session. So so far, we have been through the different basics of supercapacitors and other energy storage devices, especially supercapacitors. The working of supercapacitors, the various the differentiations and classifications of supercapacitors based on their energy storage processes, based on their configuration of the cell configuration, and how they store charge and what are the different compositions and contributions from different charge storage mechanisms. We just touched slightly on that part. So now we'll be discussing on that. So just before that, we need to think about different measurement systems. Those systems or measuring techniques we use to measure, that is the cyclic voltammetry, charge discharge curves of a particular electrode material first, and then for the whole cell. So first we use the 3-electrode system. 3-electrode system means we have a working electrode with the active material intact, or the active material as the working electrode. We have the counter electrode. For a single electrode measurement, that means if you are trying to characterize either cathode or anode, then we should go for 3-electrode system first, with the working electrode as the active material. With respect to a standard counter electrode, we generally use platinum wire counter electrode or platinum mesh counter electrode and a reference electrode. Now, reference electrode is for exactly measuring the potential window of the active material. That means the working electrode. Now, the reference electrode may be of different kinds. One is that saturated calomel electrode, silver chloride reference electrode. So depending on the electrolyte and depending on the pH of the electrolyte, you can change the reference electrode as you need. So 3-electrode system is much better as compared to 2-electrode system in measuring the working potential of any of the individual electrodes, either cathode or anode, precisely because the working electrode voltage is measured with respect to the standard potential of the reference electrode. So this is the way we do single electrode characterization in 3-electrode system. Now, once you characterize the single electrodes, or that means in cathode and anode both, through the 3-electrode processes, you should go for making a symmetric cell or the asymmetric cell. In that case, what do you do? That is called the 2-electrode system. So this is 3-electrode system is for using or for characterizing half cell. Half cell means either cathode or anode material. 2-electrode system is used for measuring full cell. In symmetric configuration or in asymmetric configuration, or in the full cell configuration, what we do? We just short the counter and the reference together so that we have one working electrode as a anode or cathode and the other one the counter electrode. That means either cathode or anode respectively. So 3-electrode system for half cell measurements, 2-electrode system for full cell measurement. So advantages of nanomaterials for supercapacitor electrode. We have already discussed different prerequisite of electrode materials, just like their high cyclability, long-term stability, chemical stability, structural stability. There should be high surface area, because higher the surface area, higher will be the charge storage sites, those we call as a reaction sites, and higher will be the capacitance, higher will be the energy density, and so on. Good electronic conductivity refers to the electron should move during the electrochemical processes. Electron should move unhindered so that total resistance of the system should go down. Okay, so material should have high specific surface area and higher electronic conductivity. It should be temperature stable, higher temperature stable and cost effective. Now, why nanomaterials? Because if you go down from bulk to nanoscale, we increase the aspect ratio. That means the aspect ratio. That means that we increase the surface to volume ratio. Higher specific surface area, that means higher surface to volume ratio, will boost the electrochemical reactions or molecular absorption. That means higher the surface area, higher will be the reaction sites, higher will be the capacitance, higher will be the energy density. Those are correlated. This is the number one. Nanomaterials give rise a larger surface to volume ratio as compared to their bulk counterpart. Give rise to porous structure. Okay, because there will be a lot of defects in the sample whenever you are making nanomaterials from top down to or using top down or bottom up approaches. You can create a lot of defects, a lot of pores inside those systems or inside those materials. So those pores or those defects will act as reaction center. That means you can increase the number of reaction sites further, and those pores will further allow ion infiltration, or you can think of the ion will easily penetrate through those pores inside the material itself. That means hide the reaction sites. And you can actually, and it is obvious that by tuning the size of the nanomaterial, you can tune their fundamental properties without changing the chemical composition. So these are the different characteristics we look for in a nanomaterial before being used as a supercapacitor electrode. So mainly two things: higher surface area, good electronic conductivity. And that is the reason. Okay, and again, I just want to revisit this term because whenever we'll be dealing with these materials, we'll be talking a lot of these different measuring parameters like capacitance, rate performance, energy density, power density, and cycle life. Okay. And one thing I just want to repeat, that when to use specific terminology and areal or volumetric terms, because capacitance can be represented in terms of specific and in terms of gravimetric way. That means specific means farad per gram, gravimetric means or areal means farad per semi squared. So if you are thinking of a bulk sample, that means in terms of having weight around 2 to 3 milligram or to 5 milligram or higher, you should represent the capacitance or any other parameter like energy density or power density in terms of farad per gram. That means in specific terminology. However, if you are thinking of making thin films, okay, making thin films as the electrode material, having thickness maybe in micrometers, so you should definitely think of representing the different performance parameters in terms of areal. That means farad per semi square or farad per semi cube, either areal or volumetric way. So these are the things you should keep in mind for presenting your capacitance or corresponding energy density and power density parameters. Okay, so that the one thing that we are discussing, the material, the electrode material should have very high surface area and high electronic conductivity. And you know that EDLC, the pseudo capacitors have much higher energy density and power density as compared to electrical double layer capacitors. So we are mainly focused on pseudo capacitive material. So the first pseudo capacitive material that was studied a lot was ruthenium oxide, because it has three redox peaks, or it goes through three redox mechanism during charging and the discharging processes. That gives you a huge capacitance. Okay, this is the first one. And second one is that it has a very good electronic conductivity. Ruthenium oxide is a very good electronic conductor. So we match the two main criteria of an ideal capacitive or the pseudo capacitive material in ruthenium oxide. Very high surface area. If you make a nanomaterial of ruthenium oxide, it will give you very high surface area. It has high redox activity and high electronic conductivity. So every criteria is there for ruthenium oxide. So ruthenium oxide was well studied in 10 to 15 years back, but the main problem with ruthenium oxide, it's very costly. It is very much costly as compared to other transition metal oxides and carbon, obviously. So this is the main reason ruthenium oxide has not been used so far for large scale fabrication of supercapacitors. So after having a lot of interest in ruthenium oxide, so just because of the cost effect, people have moved from ruthenium oxide to other transition metal oxide. The second transition metal oxides, well-studied transition metal oxide, is manganese oxide, especially MnO2. It is a very good redox activity. It has a very good redox activity, but its electronic conductivity is not that much. Conductivity is poor, and it is low cost because it is earth abundant. Manganese oxide is earth abundant. It has a very good good redox activity, low cost material, but problem is with its electronic conductivity. It's almost insulating in nature. So in manganese oxide, this is a CV curve of a manganese oxide electrode, okay, and y-axis is the current, x-axis is the voltage. So it is happening like this, that it shows a almost rectangular CV curve within the potential window from between 0 and I think 0.9 volt. But you see the CV curve is almost identical to that of the EDLCs, that means electrical double layer capacitors or carbons. But the response is same, the rectangular CV curve, but the process is different. Here the manganese oxide stores charge through successive redox reactions, which are represented by these ellipses, okay, within this whole potential window. So these are successive redox reactions happening within this whole potential window, and as a whole we are having this square shaped, almost rectangular shaped CV loop for manganese oxide. But manganese oxide, remember, manganese oxide is pseudo-capacitive. Redox reaction, it stores charges through redox reactions. So it is pseudo-capacitor. So the problem, the manganese oxide can show, I think the capacitance is almost, you can go beyond 200 farad per gram or even more than that by different nanostructures, by using different nanostructures as the electrode material. So it is the manganese oxide. After ruthenium oxide, the most studied transition metal oxide is manganese oxide. So after this manganese oxide, we are a bit careful about choosing electrode material, that which material we should go with for further electrochemical measurements. So we choose another earth abundant material called hematite. Hematite is alpha Fe2O3, just like the other two variant of iron oxide, and it is, first of all, it is safe, it is perfectly safe, it is cost effective because you can see iron oxide almost every place, and it has a very good redox activity. That means it can also, it has two, in case of iron oxide, iron is in 3+ state. So when it charges or discharges, it the oxidation state moves from 2 to 3. Okay, so it has a good redox activity, good electronic conductivity, I think much better than manganese oxide, and it is earth abundant material. So we can use iron oxide as the electroactive material. So what we did, we used, or we prepared hematite nanorods, that means iron oxide nanorods. We prepared iron oxide nanorods on different substrates. Substrates means you can use current that carbon cloth, or you can use stainless steel. So these are the ACM images of iron oxide nanorod fabricated on carbon cloth substrate. So here just remember, carbon cloth is will act as a current collector or substrate, the same thing. So you can just simply prepare it through some hydrothermal process. You take I think iron chloride and sodium sulfate, you do some hydrothermal process, and you can get this iron oxide nano. First you prepare iron oxyhydroxide, Fe-OOH, and then you heat it to get Fe2O3. So this process you can do it by hydrothermal technique. You can prepare iron oxide nanorods, which are actually yellowish in color, and then you heat it to get iron oxide. So we prepared this iron oxide nanorods by hydrothermal method using on carbon cloth substrate, and then we went for the electrochemical measurements. Because we are talking about single electrode measurement, so we used 3 electrode system. So iron oxide nanorod we used as a negative electrode material because it shows some good redox activity within the negative electrode side. So this is, we characterize this system between 0 to -1 potential window. So you can see the CV loop is not a perfectly rectangular one, or it's not a perfectly Faradaic one that usually shows this kind of oxidation and reduction peaks. So it is somewhat in between, because you can see some redox peaks in here, and also in here. So this is a perfect representation of a pseudoactive material. You have both the characteristic from EDLC and the Faraday contributions. So it shows this kind of CV behavior or current voltage characteristic within the negative potential window. And when we calculated the capacitance, it shows almost 220 millifarad per semi square, because we deposited a thin film of iron oxide on carbon cloth. So we prefer to use the capacitance, or represent the capacitance in terms of gravimetric values. That means millifarad per centimeter square. So it shows around 220 millifarad per centimeter square. But using the loading density was almost 1 milligram per semi square. So it represents almost 200 to 210 farad per gram. So almost similar in terms of areal capacitance and specific capacitance. And this variation of areal capacitance with the scan rate, this is called rate performance. That we discussed a few slides back, that by changing the rate of scanning the voltage, how the performance is changing, that how different these areal capacitance or capacitances are. This is called the rate performance. So this is the hematite as the negative electrode material. But is it possible to use hematite as a positive electrode material also? But if you consider simple hematite, or if you measure simple hematite as a positive electrode material, the redox activity is not that much. It shows a very negligible specific capacitance or areal capacitance. But we can use hematite nanorod in the negative electrode, in the positive electrode, but not as an active material, but as a host or substrate. How? Let's see. So we use hematite nanorod as positive electrode material, not the electroactive material, a part of the electrode material. So what we did, we took the same thing. We took the same iron oxide nanorod, deposited on carbon cloth substrate, and this is a single fabric of the carbon cloth. This is schematic diagram. And what we did, we coated these nanorods, iron oxide nanorods, with manganese oxide. So this is some kind of electrodeposition of manganese oxide onto iron oxide nanorods fabricated on carbon cloth. So this is a core shell structure, where iron oxide is the core and manganese oxide is the shell. Okay, so the idea of this core shell structure is like that. Iron oxide has the electronic conductivity which is higher than manganese oxide. Iron oxide has the electronic conductivity which is higher than manganese oxide. However, manganese oxide has the redox activity much better than iron oxide. Okay, and manganese oxide shows redox activity in the positive side, whereas iron oxide shows redox activity in the negative side. So we used this core shell structure as the positive electrode material. So what our idea was that all the redox activity or the redox mechanism for charge storage will be happening on the manganese surface. So MnO2, it will move from Mn4 plus to Mn2 plus, and through different oxidation states. It will move through different oxidation states by oxidizing and reduction reactions. So that means charge storage happens within the Mn surface, but at the same time, as iron oxide has better electronic conductivity than manganese oxide, so electron will move through the core, which has a higher electronic conductivity as compared to manganese oxide. the electron will move through the core and pass through the current collector. This is called current collector. In our case, this current collector is carbon cloth. So redox reaction happens at the surface, manganese dioxide, but during the time, whatever with the electron transfer is taking place, those electrons are moving through the core, which is iron oxide, and moves to the current collector and to the outer circuit. So that was the idea. So in this way, we can use iron oxide nanorod in the positive electrode side also. So what was the advantage in terms of CVCD? Okay, this is actually the SEM image. This is the SEM image. The left hand side image is the SEM image. This shows manganese dioxide coated iron oxide, and this is the TM image, which again shows the thin layer of manganese dioxide shell on iron oxide core. So in terms of electrochemical performance, the black one, it is the comparison of CV of different configurations in the positive. Just see, this is in the positive electrode side. The black one, the black CV loop that represents the CV of iron oxide. So as I told you, iron oxide shows negligible redox activity in the positive electrode side. Okay, the red one shows the activity of manganese oxide, and the blue one shows the redox activity or the activity of iron oxide manganese dioxide core shell structure. So you can see by this kind of electrode architecture, or this kind of by making this kind of electrode architecture, you can improve the electrochemical performance to a significant extent. So this is the case of so here we have used the iron oxide in both the negative side and the positive side of the electrode materials. After that, what we did, we have gone for the fabrication of asymmetric supercapacitor. Just remember, asymmetric capacitor means positive and the negative materials are made of different materials. Here the negative material is iron oxide, positive material is manganese dioxide coated on iron oxide. So you can see side by side comparison of their working potential windows. Iron oxide operates in the negative side, manganese dioxide operates in the positive side. So this is the symmetric configuration. However, before making this asymmetric supercapacitor, you have to do some calculation that is called charge balance calculation. This is very important because asymmetric supercapacitor, the materials are different, so they have different storage capacity. Okay, but you see, when you combine positive and the negative electrode, you make a series combination, and in case of a series combination, the capacitance is inversely proportional. 1 by C equals to 1 by C1 plus 1 by C2. In this case, you can get the maximum capacitance when C1 and C2 are almost equal. If there is a significant difference between C1 and C2, that means capacitances of cathodes and anode, the overall capacity will go down. So the optimal condition is that C1 and C2, that means the capacitance of both the materials should be equal, almost equal. In that case, what we do, and this is actually a critical condition for asymmetric one, because the materials are different. In case of a symmetric, materials are same, no need of charge balance. Here we do what we just equal the charges on the cathode side with the anode side. Q plus and Q minus. Q plus means C plus V plus Q equal to CV, and if the mass of the material is M plus, it's like that, and this is C minus V minus, mass is like this. So you can calculate M plus by M minus equal to C minus V minus by C plus V plus. So now you know the values of C minus capacitances and operational potential window for cathode and anode material. From this ratio, you can find out the ratio between M plus and M minus. That means mass of cathode and mass of anode. What should be the optimal ratio? You just maintain that ratio. That means you are balancing the charges on both sides of the electrode material, and you are having the maximum capacitance utilizing this equation. So whatever the asymmetric supercapacitor we prepare, we go through this charge balance calculation first. So here also we did the same thing, and you can see the area under the curve, these CV loops are almost similar. So it is the result of the charge balance calculations. Okay, so after this charge balance calculation, we did the CV for the full cell. Full cell means in 2 electrode system. That means by shorting counter with the reference. So the iron oxide was active from 0 to -1, and manganese dioxide was active from within 0 to +1. So we can extend the potential window of the asymmetric cell up to 0 to 2 volt. 0 to 2 volt. Okay, and you can even think of going further. You can have 0 to 2.1, 2.2 even. Okay, so this is the idea and utilization, or you can say the effectiveness of assembling asymmetric cell over symmetric one. You can extend the potential window by combining the potential windows of individual. So it is iron oxide, manganese dioxide, asymmetric supercapacitor with a operation potential window of 2 volt. Fine. Next, we and this kind of core shell structure design, we extended that design further to prepare this kind of zinc oxide Fe2O3 core shell and nanorods also. I think the slides are. Am I audible?
Yes, sir. You are audible, sir.
Am I audible?
Yes, sir. You are audible, sir.
But I think the slides are not changing, right?
Yes, sir. So right now I'm seeing your hematite-based asymmetric supercapacitor slide.
Yeah, but I am changing the slides, but it is not changing.
Sir, I guess you can escape this window and reshare the slides.
Okay, just a minute. I am sharing the window, but it is not showing.
So it's showing that you have started the screen sharing, but slides are not visible yet.
Yeah, slides are not visible. I don't know what is happening.
I guess it is just poor connectivity.
Actually, that was the reason I shifted to my mobile network. LAN network is even poor. Just let me check.
Yeah, sure, sir.
It's not showing. Just to give me a minute.
Sir, we can try another thing. You just disconnect this Zoom meeting and join it again. I guess that will work. Sir, am I audible to you, sir? Sir, please unmute yourself, sir. Sir, unmute yourself. Debasish sir.
Yes, and I think now it's
Yes, sir. You are audible, sir, and your PPT is also showing.
is it? Yeah.
Yes, sir. Yes, sir. Slides are changing and it is visible.
Yeah, but yeah, I think but it's a bit slow. Okay, I'll try to move it fast. Let's see. Sorry for the interruption. It is actually moving slowly. Okay, let's see. Sorry for the interruption, just because of the poor network connection. So the core shell nanorod structure again. So we extended the idea to prepare that zinc oxide Fe2O3 core shell nanorod. We first prepared the zinc oxide nanorod, these hexagonal nanorods you can see, and on stainless steel substrate, and we made a thin film of iron oxide on this zinc oxide nanorod to make this kind of core shell structure. Okay, so this is the TM image of one of the core shell zinc oxide iron oxide nanorod. So the center part is zinc oxide and outer part is Fe2O3, which is represented by different colors of zinc and iron. So the process was just by drop casting of iron chloride on zinc oxide nanorods. You drop cast the iron oxide on the ferric chloride on zinc oxide nanorod, and do it multiple times and just heat it at 300 degrees centigrade just to transform iron chloride into iron oxide. So this is a core shell design strategy, and after that we did some electrochemical analysis of this core shell structure. You can again see this zinc oxide in the negative side showing negligible electrochemical property, this black one. Iron oxide shows some better property, as iron oxide is electroactive in the negative side only. But if you think of this core shell structure, it shows much better property as compared to both zinc oxide and the iron oxide, because the current density has gone significantly up when you made the core shell structure. So in terms of capacitances, you can see this table here. So Fe2O3, it shows a capacitance of 295 farad per gram. Core shell structure shows 492 farad per gram. Okay, this is almost double the capacitance at 10 millivolt per second scan rate. And the graph shows the rate performance of iron oxide and the core shell structure when the scan rate was changed from 10 millivolt per second to 400 millivolt per second. So there is a significant jump in the specific capacitance for the core shell structure as compared to the pristine structure. And this is the effectiveness of effectiveness of having core shell structure or designing core shell structure. So one part is storing charge, and the second part is acting like a fast or acting like a highway for fast movement of electrons. So after making this core shell structure as the negative electrode, we prepared zinc oxide carbon as the positive electrode. So we just coat this zinc oxide with the carbon material. You can do it by deep coating zinc oxide into a solution of, I think, glucose, into a solution of glucose, take it out and just burn it. So glucose will become carbon and you can make zinc oxide carbon core shell structure. And we prepared this asymmetric cell after the charge balancing, obviously. So this is a cross-sectional area or the cross-sectional view of the zinc oxide Fe2O3 and zinc oxide carbon asymmetric supercapacitor. And in this supercapacitor, asymmetric capacitor, you can see we can move up to, we can get a voltage up to 0 to 1.8 volt. Whereas the individual electrode, that means iron oxide, could go up to only 0 to -1 volt. So by making asymmetric capacitor, we can increase the potential window to a significant amount. That means increase in energy density. So these are just related to core shell structure having one-dimensional nanostructure. Next, I would like to show that how you can anchor pseudo-capacitive material onto different carbon-based materials, let's say for CNT. So we took this multi-walled CNT and we anchored manganese oxide as well as iron oxide with this CNT substrate. That here the TM images show you the manganese oxide anchored on CNT substrate. We did or we fabricated this system by simple, it is called a manganese or metal hexacyanoferrate derived material. That means if you take manganese hexacyanoferrate, or you can actually, it is called the process is a reduction of manganese hexacyanoferrate on CNT. It will give rise to manganese oxide on CNT. If you take iron hexacyanoferrate, it will give rise to iron oxide anchored on CNT. Okay, in both way, you can use the same process, but simply by changing the precursor material, iron hexacyanoferrate and manganese hexacyanoferrate, you can derive iron oxide nanoparticle and manganese oxide nanoparticle anchored on CNT. Why did we do it? Just to improve the performance. Here in the CV, so because CNT is highly conductive and manganese oxide and iron oxides are pseudo-capacitive in nature, but they are in terms of resistive because they are oxides, but CNT is conductive. So we made these combination a composite material to improve the total conductivity as well as the pseudo-capacitive property. So the CV, here the CV shows, the black curve shows the performance of CNT and the red curve shows the performance of CNT Mn3O4. That means the improve is significant after making the composite material. And this is also represented in terms of specific capacitance. In the second figure, where specific capacitance is plotted in terms of current, that means it is a kind of rate performance or comparison of rate performance. These two graphs shows definitely that there is an improvement in performance after anchoring these oxide, transition metal oxides on CNT surface. So we prepared manganese oxide on CNT and iron oxide on CNT. So iron oxide works on negative side, manganese oxide works on positive side. Then again, we fabricated the asymmetric capacitor. And we did the same kind of electrochemical characterizations. And we have found out that these asymmetric capacitor We call it a hybrid asymmetric capacitor or normal asymmetric capacitor. It can show stable electrochemical behavior within a potential window of 0 to 1.8 volt. Okay, we started from 0 to 8 volt because manganese oxide anchored on CNT that worked well within 0 to 0.8 volt. So after combining these two or making this asymmetric one, we could go up to 0 to 1.8 volt. In just remember, until till now we have only used aqueous based electrolyte. So using aqueous based electrolyte and having a potential window close to 2 volt is a huge achievement. Or you can move again up to 2.4 volt with aqueous electrolyte if everything remains perfect. But I think 2 to 2.1 volt is achievable very easily. So we started with the nanorod, then we moved towards the CNT and CNT and the pseudo capacitive material composite, and then we actually applied these hybrid asymmetric capacitor. That means CNT, Fe2O3 CNT, Fe2O3 MnO2 for different purposes. These asymmetric capacitor can be used to power a red LED, can power a blue LED, as well as it can actually charge a mobile phone for a few seconds. So that means the figures are just for representation purpose, but we applied these ASC for this kind of applications. So starting from nanorod, then one-dimensional nanotubes, CNT nanotubes with combination of some pseudoactive material. I would like to show you the supercapacitive property of a two-dimensional material, which is layered MOS2. MOS2 is a very interesting material because it has layered structure. Okay, and depending on its certain crystallinity, it can show it has a hexagonal 1H phase, which is semiconducting in nature, and a much popularized 1T phase, which is metallic characteristic, which is metallic in nature actually. So whoever has used MOS2 so far, they are mainly interested about their 1T phase because it is metallic in nature, much higher conductivity as compared to hexagonal 1H phase. But the problem is that to make 1T phase of MOS2, you first need to start with 1H MOS2. Sorry, this is actually 2H phase, not 1H phase. You have to start with 2H MOS2, 2H phase of MOS2 to get 1T MOS2. But the problem is that 1T phase is not a stable phase. 1T phase reportedly transforms from its 2H counterpart by different mechanism. This is called lithium-ion intercalation process. However, this 1T phase is not a perfectly stable phase. It goes back to the original 2H phase in time. However, you can stabilize this 1T phase by substitutional doping and covalent functionalization, as also by introducing strain in it. That means you need to actually keep those layers separated from each other to make the 1T phase stable. It can be done by that lithium intercalation. It can be done by some other kind of doping or functionalization, that kind of thing. So getting or just keeping this thing in mind, we went for fabricating two-dimensional MOS2, mainly the two-dimensional MOS2 nanosheet, which has 1T characteristic. That means you can think of 1T MOS2 nanosheets. Okay, and how to expand the interlayer? Idea was to expansion of interlayer spacing of MOS2 nanosheets in order to ease intercalation and deintercalation of electrolytic ions to enhance the capacity performance. If you increase the interlayer spacing, ions can move easily, go inside and come out very easily. Okay, that will give rise to higher values of capacitance or pseudo capacitance. So we prepared this freestanding MOS2 RGO hybrid nanoflakes on MO substrate. By hydrothermal method, we took molybdenum foil and a mixture of thiourea and graphene oxide solution. And we did the hydrothermal for 180 degrees centigrade for 18 hours. And what we got is a thin film of MOS2 RGO composite on MO substrate. Here this thiourea, it acts primarily as a sulfur source. So we don't need to add a sulfur precursor. Thiourea, or the additional source of sulfur, we don't need to add. Thiourea acts as a sulfur source and it gives rise to these ammonium ions, NH4 plus ions during the hydrothermal process. So these ammonium ions can intercalate within the layers of MOS2. Okay, and it can increase the separation and keep the 1T phase stable. And this separation can also be enhanced by the presence of RGO. So that means ammonium ions, in addition to RGO, they facilitated the in situ exfoliation of MOS2. So we get exfoliated MOS2 through this standalone process. So then we were doing some SEM and TM characterization. So the image A shows the SEM image. These are nanoflakes. B, from B to D, they show the TM images, where you can see the interlayer spacing between MOS2, different MOS2 layer is 0.91 to 97 nanometer. Okay, in general, the interlayer spacing for MOS2 which are not exfoliated is within range of 0.5 to 0.6 nanometer. But just because of the presence of ammonium ions and RGO, the interlayer spacing has extended to this extent, 0.91 to 97 nanometer. So then we went for doing some electrochemical analysis, just starting with cyclic voltammetry, then charge discharge measurements, and so on. So this image shows the comparison of CV property, that is a cyclic voltammetry for MO foil, MOS2 on MO, and MOS2 RTO on MO. You can see MOS2 RTO shows the highest capacitance or current, that means the capacitance, as compared to all the other components. That means composite shows much better electronic activity or redox activity as compared to its component materials, which was our idea actually. And then we do the CV, and then we measured the rate performance for this MOS2 RGO hybrid material. The rate performance is really well. It shows a capacitance of a volumetric capacitance of around 350 farad per semi-cube, and very good rate performance, which is much higher or much better than pristine MOS2. Okay, then coming to the charge storage mechanism, because we are interested in how much charge is stored and what are the different processes governing the charge storage mechanism, or different processes happening within this MOS2. So we have already discussed that MOS2 stores charge through Faradic reactions and non-Faradic reactions. So how to actually differentiate these things and take out their individual diffusion independent process is electrical double layer. Faradic diffusion independent process is called pseudocapacitance, and Faradic diffusion control process is called Faradic process. So Faradic diffusion independent and non-Faradic diffusion independent, they are together. We can actually separate diffusion independent and diffusion controlled processes. For that, we have to use this equation, because for a diffusion independent process, current is proportional to scan rate directly, and for a diffusion dependent process, current is proportional to V to the power half. Okay, by satisfying Cottrell's equation, if we do this kind of mathematics, you can find out the capacitive contribution, the purely capacitive contribution, that means diffusion independent processes. And you can actually segregate the diffusion independent contribution at each and individual potentials using this equation. However, this equation can't separate out these two things, pseudocapacitance and electrical double layer capacitance, because pseudocapacitance and electrical double layer capacitance are both resulted from diffusion independent processes. Okay, through earlier measurements or through earlier calculations, we segregated diffusion controlled and diffusion independent processes, but pseudo diffusion independent processes include pseudocapacitance and electrical double layer capacitance. So how to separate these two contributions? For that, we used this called the impedance analysis, or electrochemical impedance spectra. We took the EI spectra. These are called Nyquist plot at different potential windows, starting from -0.1 to -0.9, and we fit those data with this with a equivalent circuit model. Okay, in the equivalent circuit model, we have electronic resistance. This is double layer resistance, CPDL, and this component is pseudo capacitance. Sorry, this is double layer capacitance. CP pseudo means pseudo capacitance, and CPW, it is related to some kind of Warburg, is called Warburg element, and RCT is called charge transfer resistance. So if we fit these graphs, these Nyquist plots with this equation, with this circuit model, we can get the values of CPDL and CP pseudo. That means double layer capacitance and pseudo capacitance at each of these potentials. If we do that, you can actually separate the pseudo capacity part from the double layer part at different potential windows. So utilizing CV analysis and electrochemical impedance spectra, that means Nyquist plot, you can take out or segregate individual parts, diffusion controlled, diffusion independent, pseudo capacitive, and double layer capacitance from these things. So these are simple calculations or mathematical calculations and a bit of fitting, circuit fitting. After this thing, we prepared the asymmetric capacitor again, because we have already prepared manganese dioxide and iron oxide potential structure. We combined with MOS2 RGO, and we had a potential window between 0 to 2 volt. We had a potential window between 0 to 2 volt for this thin film based asymmetric supercapacitors. It shows excellent cycle life, up to 20,000 cycles, almost 100% capacitance retention. And this thin film based supercapacitor can also be used to light or to power a red LED for a few minutes after being charged for a few seconds. Okay, I'll just take a few more minutes. Not much.
Sure, sir. So please take your time, sir.
Okay, in that case, I can explain this thing a bit.
Sure, sir.
Yeah. Okay, so this is actually the total charge storage mechanism in MOS2 RGO and iron oxide, manganese dioxide, asymmetric supercapacitor. So MnO2, this part is the positive electrode part, Fe2O3 MnO2 crystal structure. MOS2 RGO is the negative electrode part. We combine these two, we get a thin film based asymmetric supercapacitor. So when these things charge and discharge, so iron oxide or manganese oxide stored charge through redox mechanism from Mn4 plus to Mn3 plus to Mn2 plus, like that. And during the time the electron moves through this iron oxide core to the current collector, which is carbon again. But in the same time, in case of the MOS2 stores charge through Faradic and non-Faradic processes. Surface related Faradic and non-Faradic means EDLC and pseudocapacitive, and the intercalation related bulk process, that means Faradic process. So by this way, the manganese the MOS2 RGO and Fe2O3 MnO2 store charges in this asymmetric supercapacitor, and we have a potential window of 2 volt here. Okay, so up to this point, we have mainly focused on different transition metal oxides and their composites with carbon mainly. And transition metal oxides means iron oxide, oxide and sulfide, iron oxide, nickel oxide, and MOS2 other material. So far, and we used mainly aqueous electrolyte, so that the asymmetric supercapacitor, whatever we have produced, it has a maximum cell voltage of 2 volt, just because of the limited working potential with the aqueous electrolyte. And they show specific energy density within 50 to 60 watt-hour per kg, with a specific power density of 1 kilowatt to 10 kilowatt per kg, and which is represented by this red marked area. So this red marked area shows the results of our work so far, and how these performance compare with the other reported values of capacitor, lithium-ion batteries, and electrochemical capacitors in this Regon chart. This is the Regon chart. So our next idea, or our present work, is mainly focused on how to increase this energy power density further. So we need to move from this red shaded area to this black shaded area. That means whatever we did so far, they can match the power density of the electrochemical capacitor, but the energy density is not that much. Okay. But what we need to do, we need to further increase the energy density to match up with the energy density with the lithium-ion batteries or lithium primary cells, these things. So that means our idea, okay, and that can be reached by making hybrid ion capacitor having a cell voltage over 4 volt. That means we have to use organic electrolytes or non-aqueous electrolytes. Performance of the hybrid ion capacitor can be more than 100 watt-hour per kg, with a specific power between 1 kilowatt to 10 kilowatt per kg. And I can show you a general schematic diagram for a hybrid ion capacitor that we are working on right now. We are mainly working on fabricating different kinds of carbon materials, which can be used in both the anode side and the cathode side. In the cathode side, the carbon materials, these carbons are called heteroatom doped carbons, means nitrogen doped, boron doped carbon. This is the capacitive side. This is the capacitive side of the hybrid ion capacitor, which is made of high surface area carbon material. In the anodic side, you can directly use carbon materials. However, to further improve their energy density, you can think of making carbon transition metal oxide composite, transition metal oxide and carbon composite, and to use in the as the battery type anode. So you can use carbon in both the sides, but in case of an anode side, you can make some composition with some transition metal oxides. It's up to you. So by this way, you can make a hybrid capacitor, and just by using some organic electrolytes, you can achieve a potential window in excess of 4 volt. That means increase in energy density more than 100 watt-hour per kg. So this is our goal. So we are working on that, and the PhD students working with me, they are mainly focusing on fabricating different types of materials from different biomasses or metal organic frameworks. And the PhD students, mainly Yogita, Hemkanwar, and Mr. Himanshu, they are working on making this kind of carbons, surface area carbon, and also Mr. Hariram, who was a project student, just left our group few months, the last month. They are doing a lot of work in first designing and then fabricating different carbons, porous carbons and heteroatom rich carbons from different precursor material, including biomasses. So all of the acknowledgement should go to them. Apart from that, my sincere thanks to my postdoc supervisors, Professor Ashok Shukla and Professor D.D. Sharma from Indian Institute of Science, Bangalore. My sincere thanks to my students who are working a lot in this area of fabricating hybrid ion capacitor. Different funding agencies, MNIT, DST, SCRB, and ISRO, and also the organizing committee member for this workshop, and for inviting me in this workshop and giving me the opportunity to deliver my work or our work in this workshop. So with this, I would like to conclude. So now the session is open for questions. Thank you.
Thank you so much, sir. Sir, our first question is from Ms. Mamta Patel, and she's asking, how do we decide whether a particular type of electrode material is to be used as positive or negative electrode?
Okay, so first, if one should just go for checking that if we don't know about their redox activity, we should what we do, we just go for their CV and CD categorization in the positive and the negative potential window. But if we don't know the redox activity of that particular material at all, in that case, we go for checking in the positive potential side and the negative potential side, and then find out that in which side it shows better behavior. Otherwise, if we know about their redox activity, that means in which oxidation state that particular element is, then you can find out that whether you go for reduction first or oxidation first. That in case of iron oxide, if it is in the Fe2O3, it has 3+. So you can't oxidize it further to Fe3+ to Fe4+. So what we need to do, we need to first reduce it from Fe3+ to Fe2+, right? That is the reason we go in the negative side, just like that.
Thank you so much, sir. Sir, next question is, can we use biochar-based carbon material as electrode material? If doping is required, then what type of dopant can be used?
Okay, yeah, this is a very interesting topic. Biochar and again biomass materials, and if you pyrolyze this thing, you can get very high surface area carbon, and you should definitely go for that. And if you go for some novel biochar materials, it's completely fine. You should definitely try it. And if you want to dope to further increase the conductivity as well as the capacitance, you should think of some heteroatoms called nitrogen, boron, this kind of things. So you can dope nitrogen, boron, and etc. to improve the performance further.
So, sir, in that case, can we prepare a symmetric or asymmetric type of supercapacitor? Like if we are using only the carbon material?
Okay, you can try it in both the ways. You can go for making symmetric one. Okay, but it will be limited, but the potential window will be limited in that case. So if you need to increase the potential window, you should definitely try for asymmetric one. And in that case, you can think of making a composite of that carbon with some transition metal oxide on other pseudocapacitive material. Then you can combine that composite with the carbon to make an asymmetric capacitor with much higher potential window.
Thank
So
you, sir.
both the ways it's fine.
Yes, sir. So next question is it mandatory to use transition metal oxide in the electrode material as base or dopant?
As sorry, I couldn't get the last part.
I guess he wants to ask, is it mandatory to use transition metal oxides in any form in the supercapacitor?
Actually, transition metal oxides are the redox active materials. You can use transition metal oxide, transition metal nitride. Actually, pseudocapacitive component, they have much higher energy density and capacitance as compared to EDLC. So this is the reason we, in general, prefer pseudocapacitive materials as compared to EDLC. This means the carbon-based materials. Either you go for completely pure pseudocapacitive material, just like transition metal oxide or nitride or carbide. Otherwise, you make a composite and you get better performance as compared to the individual components. It is not necessary, but it is preferable if you want to increase the efficiency or capacity and energy density.
Thank you, sir. Next question and the last question is how hybrid supercapacitors can be designed for good performance? What factors should be kept in mind?
Hybrid supercapacitors, you can think of first, asymmetric supercapacitor is a hybrid supercapacitor. Okay, and that we have discussed so far that you need to first go for the electrode materials, that which material you can go for a composite, a asymmetric supercapacitor made of a pseudoactive material and a carbon, or two different pseudoactive materials together. You can design the asymmetric supercapacitor like that by taking different combinations. Okay, this is the normal asymmetric supercapacitor with aqueous electrolyte. You can use aqueous electrolyte because it is easily available. It is very easy to handle with. But the problem is with the electrode, the cell potential. You can't move beyond 2.1 to 2.2 volt. So in that case, you can go for using organic electrolyte, right? Having a wide potential window of 4 volt. You use the same material as positive and the negative electrode, but just simple change the electrolyte from water or aqueous to organic. So you can increase the potential window from 2.2 volt to 4 volt. That means improve the energy density. So you first decide about the material, that which material you should definitely go with further, and then the electrolyte for overall enhancement of the energy and the power density.
Thank you so much, sir, for such nice explanations. We are so thankful to you, sir, that you took out time from your busy schedule and you shared your expertise on supercapacitors with our participants. I'm sure all of us have gained a lot of insight on this topic and it was a fruitful session. On the behalf of Gyan Bihar University, I extend hearty gratitude to you, sir, and all our participants. They are also expressing their gratitude towards you. I'm also thankful to participants for joining the session and being an active listener throughout. So with this, I declare end of the session 2 for the day.
Okay, thank you.